On November 5th, the orbital database refreshed. No fanfare. No headlines. Just numbers shifting in a table on the Minor Planet Center's website. Timestamp scrolling past midnight at EC, and a revised solution from NASA's Jet Propulsion Laboratory. The interstellar comet 3I, discovered 5 months earlier by the Atlas Survey Telescope in Chile, had new astrometry, new photometry, a new story encoded in the residuals. For anyone tracking this object since its July 1st discovery, something fundamental had shifted. The non-gravitational acceleration that had been conspicuously absent through September suddenly appeared in the post-perihelion data. A radial component pushing outward from the Sun at 1.1 times 10 to the minus 6 astronomical units per day squared. A transverse component at 3.7 times 10 to the minus 7. The detection stood at 37 standard deviations. Not overwhelming, and it had not been there before. This is not a story about the object changing. This is a story about the measurement changing. And in astronomy, that distinction can be as unsettling as any discovery. 3I, Atlas, arrived from interstellar space with an orbital eccentricity of 6.14. To understand what that means, consider that Earth's orbit has an eccentricity of 0.017, nearly circular. Mars sits at 0.093. Even Halley's Comet, famously elongated, reaches only 0.967. But 3I, Atlas, exceeds 1. Far exceeds it. An eccentricity above 1 means the orbit is not closed. It is hyperbolic. The object came from somewhere else, bent slightly by the Sun's gravity, and will leave forever. Its velocity at infinity, the speed it carried before the Sun's influence, and will carry again after escaping, is 58 kilometers per second. Faster than Onei, Oumuamua. Faster than Tuai Borisov. Faster than anything we have built. It reached perihelion on October 30th, 2025, at 1.36 astronomical units from the Sun, just inside the orbit of Mars, close enough to heat its surface, far enough to remain intact. At that distance, moving at 68.3 kilometers per second, it passed through the inner solar system in weeks. Ground-based telescopes tracked it from late spring through early autumn, accumulating astrometric points, positions against the background stars, measured to fractions of an arcsecond. By late September, over 4,000 observations from 227 observatories had been compiled. And those observations analyzed together showed something strange. Or rather, they showed the absence of something expected. There was no detectable, non-gravitational acceleration. The residuals, those leftover errors after subtracting the best fit gravitational orbit, were vanishingly small. 0.0288 arcseconds, averaged across months. For a comet heating up as it approached the Sun, this was unusual. Comets outgas. They lose volatiles. The escaping gas acts as a tiny rocket, nudging the nucleus off its purely gravitational path. For 3, Atlas to show no such effect suggested either that it was not outgassing significantly, or that any outgassing was perfectly symmetric, thrusting equally in all directions, producing no net force. Then, perihelion happened, and the data changed. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The update released on November 5th covered observations from October 31st through November 4th, post-perihelion. The comet had rounded the Sun, absorbed weeks of thermal input, and was now receding. The new dataset reported something the old one had not. A non-gravitational acceleration, now clearly present, decomposed into two components lying in the orbital plane. The radial term pushed the comet away from the Sun. The transverse term acted perpendicular to the Sun's direction, either speeding up or slowing down the orbital motion, depending on its sign. These accelerations were parameterized to scale with distance from the Sun following an inverse square law, the same dependence as solar heating. This is standard for cometary models. The assumption is that sunlight heats the nucleus, volatiles sublimate, and the gas escapes, producing thrust. The closer to the Sun, the stronger the effect. But the machinery behind that update is invisible. What changed between the September dataset and the November dataset was not just the calendar. It was the processing. Astrometric reductions depend on reference star catalogs. When those catalogs improve, when Gaia releases updated parallaxes, or when proper motions are recalculated, every position measurement shifts slightly. Atmospheric extinction corrections vary with season, with telescope altitude, with the humidity of the night. Photometric 0 points depend on comparison stars, and if those stars are later found to be variable, or if their magnitudes are revised, the entire baseline shifts. Background subtraction algorithms decide what counts as sky and what counts as object. For a faint, fast-moving target, that decision matters. And when new observations are added to the dataset, the orbital fit recalculates. Old points are reweighted. Outliers are flagged or downweighted based on their residuals relative to the new solution. The process is iterative, self-referential. Bend-to-build-sound. The orbit determines which points are trusted, and the trusted points determine the orbit. So when the update reported a non-gravitational acceleration where there had been none, the question is whether that acceleration was always there, hidden in noise, waiting for better data to resolve it, or whether the new processing introduced it. Change the weighting. Change the model. Change the story. Residuals are where the truth hides after the fit. They are the difference between where the object was observed and where the best fit orbit predicts it should have been. In an ideal universe, residuals are random. They scatter symmetrically around zero, Gaussian noise with no structure. But real residuals are rarely so kind. They cluster. They drift. They show periodic wiggles, slow linear trends, sudden jumps. Some of that structure comes from the instruments. Tracking errors, guiding glitches, field rotation during long exposures. Some comes from geometry. Observing the object at different phase angles, different illumination angles between the sun, the object, and the observer, can introduce systematic biases in where the brightness centered appears. And some comes from the object itself. If the nucleus is not a perfect sphere, if it is spinning, if one side is darker than the other, if jets are firing asymmetrically, those physical effects imprint themselves onto the residuals as patterns that survive the fitting process. For 3I Atlas, the pre-perihelion residuals were exceptionally clean. Averaged over months, they showed no significant structure, no drift, no clustering, just noise, tightly bounded. But post-perihelion, something changed. The residuals developed coherence, a slight but measurable deviation in the radial direction, a smaller deviation transverse to it. The updated orbital solution fit those deviations by introducing non-gravitational terms, parameters that allow the orbit to bend away from pure gravity. The fit improved. The scatter reduced. The model became more accurate in the statistical sense. But whether it became more true is a different question. Because if the original residuals were clean because the object truly was not accelerating, then the new residuals, showing structure, might indicate that the object started accelerating near perihelion. That would make physical sense. Solar heating peaks at closest approach. Volatiles that remain dormant at 4 astronomical units might sublimate vigorously at 144. The comet could have woken up. But if the original residuals were clean because the observational cadence, the atmospheric conditions, the telescope pointings all happened to align in a way that smoothed over real signals, then the new residuals might simply reflect better sampling, more observations, different filters, different instruments, different calibration pipelines. The acceleration might have been there all along, and only now is the data good enough to see it. The timeline matters. Timing in this story is not just when observations were taken, but when events are inferred to have occurred. The orbital solution places 3I Atlas at perihelion on October 30th, but that date is derived from the fit. If the fit changes, the date can shift by hours, sometimes by days. And if the timing of perihelion shifts, then the timing of everything else shifts with it. When was the object closest to Mars? When did it pass through the ecliptic plane? When did its phase angle, the sun-object observer angle, reach its minimum? These moments are not observed directly. They are interpolated from sparse data points, and the interpolation depends on the model. A revised model repositions those moments in time. Features that seem to occur before perihelion might now occur after. Brightenings that appeared delayed might now appear synchronous. Cause and effect become unstable, not because the physics changed, but because the coordinate system did. For 3I Atlas, the timeline collapse is subtle but real. The object brightened significantly near perihelion, rising by a factor of roughly 5 in the green band, centered at 0.464 micrometers. That brightening was measured, but when exactly it peaked depends on the orbital solution. If the updated solution places perihelion a few hours earlier or later than the previous one, then the brightness peak shifts relative to the closest approach. And that shift changes the interpretation. A brightness peak exactly at perihelion suggests maximum solar heating, driving maximum outgassing. A peak occurring a day after perihelion suggests delayed response, perhaps from subsurface layers heating up and releasing gas later. A peak before perihelion suggests something else entirely. Pre-warming. Internal energy. A process not directly tied to solar distance. The photometry itself is not immune to revision. Brightness measurements depend on aperture choices, how much sky you include around the object when summing photons. They depend on background subtraction, how you model the sky brightness and remove it. They depend on comparison stars, reference objects assumed to be constant. If the comparison stars are later found to vary, or if their catalog magnitudes are updated, every brightness measurement shifts. Phase angle corrections are applied to account for how the object's brightness changes with viewing geometry. These corrections assume a scattering model, how light reflects off the surface. For most comets, the model is well tested. But 3 Atlas is not most comets. Its phase angle behavior has been described as extreme. Its negative polarization, light scattered preferentially in certain orientations, is unprecedented for known comets, including 2I Borisov. If the scattering model is wrong, the phase correction is wrong, and the brightness curve becomes an artifact of processing, not a record of reality. The updated photometry shows not just brightness, but color. Near perihelion, 3I Atlas was bluer than the sun. For a comet, that is unusual. Reflected sunlight should roughly match the sun's spectrum. Dust scatters redder. But blue emission suggests something else. Ionized carbon monoxide, Co+, emits strongly in the blue and ultraviolet. If the coma was rich in Co+, the blue color makes sense. But Co+ emission requires significant gas production, and significant gas production should be visible spectroscopically. It should produce a detectable coma, a diffuse cloud of gas and dust surrounding the nucleus. Some observers reported faint extended emission around 3E Atlas. Others saw only a point source. The ambiguity persists. And in that ambiguity, the brightness data, cleaned, corrected, phase adjusted, becomes harder to trust. Not because it is wrong, but because every correction embeds assumptions, and if the assumptions do not hold, the result is a polished falsehood. Non-gravitational acceleration is the hardest signal to interpret. It requires that forces other than gravity are acting on the nucleus. For comets, the usual suspect is outgassing. Volatiles heated by the sun sublimate, gas escapes, and the escaping molecules carry momentum. By Newton's third law, the nucleus recoils. The magnitude of the recoil depends on how much gas is escaping and how fast it is moving. A typical molecular speed for water vapor at the surface temperature of a comet near 1.4 astronomical units is roughly 300 meters per second. Faster molecules mean more momentum per molecule, which means less mass loss needed to produce the same acceleration. But 300 meters per second is an upper limit for thermal velocities. If the acceleration is real, and if the gas speed is thermal, then momentum conservation demands that 3I Atlas lost at least 13% of its total mass near perihelion. 13% is enormous. It is not a surface layer evaporating. It is a significant fraction of the entire nucleus shedding into space over the course of weeks. And yet, where is the coma? Where is the spectroscopic signature of that gas? Where are the emission lines of water, cyanide, carbon monoxide. Observations with the James Webb Space Telescope in early August captured spectra showing that the coma contained only 4% water by mass diameter. 4% is far below what typical comets show. It suggests that 3E Atlas is either extremely dry or that most of its outgassing is something other than water. Nickel emission was detected, far more nickel than iron, in ratios unlike any known comet. Nickel in those proportions is common in industrial alloys, uncommon in natural ices. The puzzle deepens. If the object lost 13% of its mass through outgassing, where did that gas go? Why is it not visible? And if the gas is visible, but subtle, faint extended emission at the threshold of detection, then why does the spectroscopy show so little water? The alternative is that the non-gravitational acceleration is not from outgassing, or not entirely from outgassing. Radiation pressure can push on small particles. Dust grains lifted from the surface feel sunlight as a force. But radiation pressure scales with surface area, and 3A Atlas is large. Hubble estimates place the nucleus diameter somewhere between 440 meters and 5.6 kilometers. For an object that size, radiation pressure is negligible unless the object is porous, fluffy, or fragmenting. Another possibility is thermal recoil, the Yarkovsky effect. Sunlight heats one side of the nucleus, that side re-radiates infrared, and the re-radiated photons carry momentum. But Yarkovsky effects are tiny, accumulating over decades, not weeks. To produce the measured acceleration in the time available requires either an extremely unusual shape, an extremely fast rotation, or something else. Something else. The phrase hangs in the dataset like a shadow. If the non-gravitational acceleration is real, and if natural explanations require mass loss that is not observed, then either the observations are incomplete or the explanations are. And incomplete explanations leave room for possibilities that are uncomfortable to articulate in peer-reviewed journals, but impossible to ignore in private conversation. The silence between data points is as loud as the data itself. 3 Atlas was not observed every night. Weather, moon phase, telescope, scheduling, competing targets. The resulting dataset is sparse. Observations cluster in windows separated by gaps of days, sometimes weeks. During those gaps, anything could have happened. A brief outburst, a rotational change, a surface feature newly exposed to sunlight. The pattern we see is not the object's full behavior. It is the subset we happen to witness, stitched together across instruments and observatories, reduced by different pipelines, calibrated against different stars. When the November update changed which nights were weighted most heavily, which points were flagged as outliers, which filters were trusted, the pattern changed. Not because the object changed, but because the sampling did. And if the pattern is sensitive to which points you trust, then the pattern is not robust. It is conditional, contingent, fragile. There is a deeper issue. The update did not just add new observations. It reprocessed old ones. Astrometric solutions are iterative. When new data arrives, the entire orbit is recalculated from scratch. Points from May, June, July, months before perihelion, are refitted against the new trajectory. If the new trajectory bends differently because of the post-perihelion acceleration term, then the pre-perihelion residuals change. Features that looked real in the old solution might vanish in the new one. Features that looked like noise might sharpen into signals. The cause and effect relationship inverts. The post-perihelion data reshapes the pre-perihelion interpretation. You cannot untangle them. You cannot say which is primary. The dataset is not a linear record. It is a web of mutual dependencies, and pulling one thread tightens others. For 3A Atlas, this means the answer to whether it accelerated near perihelion depends partly on what happened after perihelion. If the comet continued to brighten, continued to show spectroscopic activity, continued to shed gas in December and beyond, then the November acceleration is likely real, a genuine physical process that began near perihelion and persisted. But if the comet faded quickly, returned to a point source, showed no further spectroscopic anomalies, then the November acceleration might be an artifact. A transient signal amplified by sparse post-perihelion coverage, misinterpreted as a sustained force. The only way to know is to keep watching. And by late December, 3 Atlas was beyond 1.8 astronomical units from Earth, dimming rapidly, receding at 58 kilometers per second. Within months, it would be too faint for most ground-based telescopes. The data we have now is most of the data we will ever have. And within that finite archive, there is a pattern. Or there was. And it changed when the reduction changed. What this tells us about the object is uncertain. What it tells us about the process of knowing is not. Every orbital solution is provisional. Every photometric curve is conditional on calibration choices. Every non-gravitational acceleration is inferred, not observed. We do not see the gas leaving the nucleus. We see the nucleus shifting slightly from where gravity alone would place it, and we infer the gas. We do not see the jets. We see the residuals, and we model the jets. And when the residuals change because the processing changes, the jets we inferred, whether they are real or imagined, change with them. The universe does not revise itself, but our descriptions of it do. And sometimes, the revision is as important as the discovery. 3I Atlas is out there now. Beyond Mars, beyond the asteroid belt, cooling as it climbs out of the sun's gravity well. It will cross Jupiter's orbit in early 2026. By mid-year, it will be among the Kuiper belt objects, though it will not linger there. By 2030, it will pass the heliopause, the boundary where the sun's wind gives way to interstellar space, and rejoin the galaxy. It will never return. We had one chance to measure it, and we took thousands of measurements, and those measurements tell a story. But the story is not stable. It shifts with each update, each recalibration, each improved star catalog. And the most honest thing we can say is that the story we tell today is the best one the data allows today. Tomorrow, the data may allow a different story. Not because the object lied, but because we are learning to listen. There is no scandal here, no error that invalidates the work, no conspiracy to suppress uncomfortable results. Just the quiet, methodical process of science refining itself. Orbits are recalculated. Residuals are re-examined. Non-gravitational terms are added, tested, removed, added again. Hypotheses are proposed, weighed against evidence, discarded or retained based on how well they predict the next observation. This is not a flaw. It is the system working as designed. And yet, it is also unsettling, because it means that certainty is always temporary, that every measurement carries within it the seeds of its own revision, that the object we think we understand today might look different tomorrow, not because it changed, but because we learned to see it more clearly. Or thought we did. The pattern changed. The object did not. Or perhaps the object did change, and we will never know, because we were not watching closely enough at the right moment, with the right instruments, under the right conditions. That ambiguity is not a failure of the method. It is the condition of the method. It is the price of trying to understand something 170 million miles away, moving faster than anything we have ever built, observed only in reflection, inferred only through math. And it is why we keep looking. Because the next interstellar visitor will arrive someday. And we will point our instruments at it, and measure its position to fractions of an arc-second, and fit curves to the data, and update those curves as new observations arrive. And we will argue over residuals, and phase angles, and non-gravitational accelerations. And the pattern will change, again and again, as the data improves. And we will do so knowing that the story we tell is not the object itself, but the best story the data will allow. And that will have to be enough. Because the alternative is to stop asking. And that is not an option.